In our introductory video, we described the TropSat mission as providing the data required to track the dynamics of mesoscale convective systems, or MCS. MCS were further characterized as fundamental building blocks in the process whereby smaller scale atmospheric features aggregate upwards into larger and longer lasting weather and climate events, some with significant societal consequence. It's the detailed sequence of physical events whereby individual smaller scale pieces become organized into progressively larger scale structures on which TropSat is focused. In this segment, we'll provide more detail on that hierarchy of pieces or building blocks. In the graphic, the vertical axis on the left will map the relative size and lifespan of each building block. Both increase as we move down the scale. As we have noted, the smallest building blocks of the ocean atmosphere system detectable by TropSat are so-called mesoscale convective systems, or MCS. MCS evolve on hourly timescales from fields of disorganized boundary layer clouds that are below the detection limit of TropSat. These are sometimes referred to as popcorn convection. For clarity, the boundary layer is the lowest layer of the atmosphere. It's defined as the layer that's directly influenced by the Earth's surface. It varies in height from day to night. It's highest during the afternoon when surface heating is at its peak. Periodically, cells of popcorn convection punch through the boundary layer. Where secondary heating of those convected parcels occurs, their warm, moist air rises further, and individual thunderstorms form. Again, while popcorn convection and individual thunderstorms are precursor states to MCS formation, both are below the detection limit of TropSat. But under environmental enforcing conditions that are not well understood, those smaller scale convective features can aggregate upward. When they do so, they form into squall lines and organized storm systems with strong surface winds, deep cloud structures, multiple convective plumes, and intense precipitation. These are mesoscale convective systems. The organization and maturation of MCS can occur over hours to a few days, and they cover hundreds of square kilometers. The processes that lead to their development are the intellectual target of TropSat observations. They matter because they continue to larger scales where they can generate the kinds of disruptive weather and climate events that affect lives and property: cyclones, floods, windstorms, but also droughts and even wildfires. These kinds of high-impact weather-related events get significant media coverage. In contrast, some of the intermediary upscale building blocks are much less well known to the public. Nevertheless, they are of critical importance in driving upward aggregation processes. One of these is called the Madden-Julian Oscillation, or MJO. The MJO is a large-scale dynamic pattern of the tropical atmosphere that has a life cycle of approximately 40 to 50 days. It was discovered in 1971 by Roland Madden and Paul Julian of the National Center for Atmospheric Research. At its origin in the Indian Ocean and into the Western Pacific, the MJO is a large-scale coupling between atmospheric circulation and tropical deep convection, characterized by aggregations or superclusters of MCS. We've seen bits of MJO activity in some of the animations shown in the introductory video. The MJO has some interesting physical traits. One is how it moves. While individual MCS entrained in superclusters move primarily from east to west, in an active MJO, the superclusters themselves move slowly from west to east. The image sequence is a time series of outgoing long-wave radiation. The dark blue indicates centers of deepest convective complexes in mature MCS. Dark orange colors correspond with convection-free regions. Note that the blue and dark blues form an eastward propagating supercluster of MCS. This marks the active phase of the MJO. It propagates slowly eastward across this broad expanse of the tropical Indian and Western Pacific Ocean basins. With MJOs, we are reaching into the medium-range forecast domain associated with considerable added value to science and society. Better understanding of MJO dynamics and the weather systems they generate would be a fundamental benefit of TropSat. Intermittently, but with important consequences to society, the daily MCS activity embedded within the medium-range dynamics of the MJO affect some of the important global scale events we've mentioned on longer, up to seasonal timescales. It's recognized that there are a variety of pathways to genesis of these events, but MJO covariability is often a common factor. And significantly, those alternate pathways are also observable by TropSat. At the largest end of these upscale transfers, the medium-range processes of the MJO impact the El Niño Southern Oscillation, or ENSO, phenomenon. ENSO is a global-scale response to increased sea surface temperatures in the equatorial eastern Pacific Ocean and along the coasts of the Americas in both hemispheres. The SST anomaly drives downstream effects that have vast global reach via processes called teleconnections. ENSO warm events, called El Niños, refer to regime shifts that occur intermittently on irregular 5 to 7 year cycles. Following an ENSO warm event, the system often overcorrects in shifting back through the ENSO neutral state, exhibiting a cooling in the tropical Pacific. This is the ENSO cold event that is often referred to as La Niña. These multi-year oscillations have strong influence over global moisture distribution, triggering multi-year droughts in some areas and prolonged periods of increased rain activity in others. Beginning with tropical convection anomalies in the western Pacific, initial ENSO development occurs over the span of about 2 years. But the anomalies in convective activity affecting the southern hemisphere are much more subtle than the large sea surface temperature anomalies on the equator that appear at the mature stage of ENSO development. Pulses in southern hemisphere convection often coincide with MJO active phase propagation through the equatorial Indo-Pacific. The dynamics and predictability of these interactions are not well known and have not been well observed as a system because of the same challenges we've mentioned previously. The anomalies occur over vast areas. The precursor or building block stages develop over short timescales, and there are many variables that are affected in the ocean and atmosphere signals at each stage of development. TropSat will be uniquely poised to address these observational challenges, and as TropSat data are analyzed and ingested into weather and climate models, we can anticipate both theoretical breakthroughs and advances in predictive accuracy. Thank you for watching this segment on the hierarchy of weather and climate building blocks, how they impact society, and how TropSat will advance understanding of the physical processes connecting them. Next, we'll cover the life cycle phases of mesoscale convective systems. Understanding how the physical features of MCS grow and change will set the stage for discussing data types that reveal their dynamics and thermodynamics.